Okay, so back then in early days of differential privacy, it wasn't clear that we could do, complicated tasks with with the constraint of differential privacy, and I think there were a few results that enhance our confidence that you can do more and more and more and more with differential privacy. And two of them were related to privacy. In 2005, we had results related to things that Adam spoke about yesterday, since the fact that you can simulate the SQ Oracle with differential privacy means that everything that is learnable in the SQ model is also learnable under differential privacy. And that's really a large class of learning problems, but it doesn't cover all possible learning problems. In particular, you cannot learn parity in this model of SQ learning. And I think that was another indication, like you can actually have a large class of problems that you can perform with differential privacy. This is work with Shiva Kasivich, Swaminathan, Homan Lee, this N guy, Raskolnikova, and Smith. So it turns out that we can bring in this idea of the Occam razor and try to do something similar with differential privacy. And this is this result. Essentially, every finite concept class can be learned privately using polynomial number of samples. We're not talking about running time yet. But in terms of sample complexity, we get that we can almost always learn as long as the concept class is finite. Okay? And the reason is going to be similar to the Occam razor result, that the sample complexity is logarithmic in the size of the concept class. And actually, the algorithm is not that complicated. We have all the tools for showing it, so let me do that. Let's begin with the finite concept class, and we get this sample of NID examples. Okay? And they are labeled according to some target concept. The learner that we'll use, in a sense, imitates, as I said, the Occam razor learner. So in the Occam razor learner, we're looking for a consistent hypothesis. And here we'll look for an almost consistent hypothesis. And the tool to do that is the exponential mechanism. Okay? So we define the score function that takes a data set and the hypothesis to be the number of points on which the hypothesis gives the correct label, okay? And the algorithm uses the exponential mechanism to output hypothesis H with probability that is proportional to this. You've seen this in Katrina's talk. That's e to the epsilon over 2 times the score function evaluated at H and divided by, we don't see the sensitivity of Q because it's 1 here, so I didn't write it, okay? Where's this thing? Here. So using properties of the exponential mechanism and putting aside the question of difference between learning over the sample and over the probability, we can get that, and this is really simple exercise, so I'm not going to do it. We can get that in sample complexity that is logarithmic in the size of the concept class is sufficient, okay? Actually, we have this second max here because we do take into account also the number of samples that is needed to learn over the distribution. Okay. And this can also be extended to the setting of agnostic learning that I'm not going to speak about today. In the setting of agnostic learning, you have no clue where the what is the labeling function. There's no underlying concept class, but you're still trying to do as best as you can with the learner. Okay. The running time may be exponential here because we apply the exponential mechanism, and in some cases this may be inherent. So here's an example, like this hypothesis labels three of the points correctly, so its score is 3. This one has the score 4, and so on. So this is not new, but what is to you today, it was at the time. But what's important is that it gives a very general result, saying that we can learn almost everything. As long as the concept class has a finite representation, we only need sample complexity that is polynomial in the size of the representation. Okay, and this leads automatically some learners, for instance. And furthermore, sorry, I didn't mention it, this gives epsilon 0 differential privacy. This is a pure privacy case. Okay. So this immediately gives a few learners. For instance, if you look at the examples that we had, then for points, we get a generic PPAC construction. You can actually run it in polynomial time, and it requires a linear in D, linear in the representation of a concept number of samples. But as we said, because the this dimension here is 1, we can do it much more efficiently without privacy. So there is a gap here. At least we can do it, and it's polynomial in the representation. With thresholds, it's similar. We can do it in polynomial time. It requires order of these samples again, but we can do it much with a lot less samples non-privately. And for parity, we're matching the bounds of the non-private case. There is an efficient construction, runs in polynomial time. And this is not a generic construction, it doesn't yield this. I'll say a few words about it soon. It runs in polynomial time. It requires order of these samples, and this is also what you need non-privately. So maybe we're off from the non-private case just by a factor of 1 over epsilon, something like that. So let me say a few words on parity. You didn't look in the slides, or? Okay, so we'll get there. So the question was whether there's a matching lower bound here for points and thresholds. We'll get there. Actually, I think with the pace I'm going, I'll go very quickly on parity. I just state what the problem is and like very quickly an idea how you could go and try solve it, but I will not give the complete algorithm. Okay, so this is the parity function, and we have this input. The non-private learning algorithm was just, maybe Gaussian elimination. We need to solve a set of linear equations. And the first question you could ask whether this is privacy preserving. There's an immediate answer, which is, what's that? Why should the answer be no? Because it's a deterministic algorithm. But maybe we can fix it. Okay. But here's a real problem. A single example can have a significant effect on the outcome of this algorithm. Okay, even if we don't do it deterministically. Think about the case where maybe we sample one solution from the space of solutions for this set of linear equations. Okay, we sample one at random. Maybe this is not deterministic. We don't see a priori why this is not good, but what we can see that a single sample can have a big effect on the outcome space. Okay? Let me, maybe in this picture. So suppose, suppose the blue dots here show the space of valid solutions for some set of linear equations, and then we introduce one more equation, one more linear equation over GF2. What happens? So either this equation constrains the output more, or it doesn't. If it doesn't constrain the solution, then we remain with the same subspace. Otherwise, if it is constraining it, then it may be that it looks like that. The third coordinate must be 0. Okay, so we're losing two solutions here. We cut the solution space by a factor of 2. Okay, is that the worst that could happen? Let's look at this thing. Maybe if we require the second coordinate to be 1, we could totally eliminate the solution space. So if we have an inconsistent equation that we add, a new equation that is inconsistent with what we've seen so far, then the solution space becomes null. Okay, a question or? So if we try to use this Gaussian elimination idea, we have a problem that in these two cases where we only are trying to apply this to neighboring data sets, we have very different solution spaces. Okay, so let me just sketch a few ideas here. In this case, the algorithm fails. Okay, so let's do this thing, and like this seems very strange. You have an algorithm. The first line says with probability 1/2 output fail and stop. Clearly, this is the line of code you should erase from your program. But if you do that, it will affect privacy, unfortunately. So with some probability, let's say 1/2, we fail. So sometimes, because of these extreme jumps in the solution space, we have to fail. So let's allow that to happen. In a sense, we want to decrease the effect of a new constraint. If it will cause the algorithm to fail, then anyway, with high probability, this algorithm fails. Okay. And the other trick, which is became to known secrecy of the sample, is that we only use about an epsilon fraction of the examples here. So we pick each one at random to be in our set with probability epsilon over 4. And then we look at the resulting set of constraints. We use Gaussian elimination. Okay, so we reduce the effect of these constraints that cause the algorithm to fail. It says we will fail anyway with high probability. So, and then we also reduce the effect of every sample on the outcome. Okay. Yeah, I think I will not get into more detail here. So certainly this is not enough. You want the algorithm to succeed with high probability. You don't want an algorithm that fails with probability 1/2 and so on. So there is more work to be done, but these are the main ideas. So let's summarize so far. We spoke about PAC learning and private PAC learning. In PAC learning, we have Occam's razor that gives sample complexity logarithmic in the concept class. It works only for finite concept classes. Or sometimes we can improve if the VC dimension is smaller than logarithmic in the concept class. And this allows us to learn some infinite concept classes. In private PAC, on the other hand, we have this algorithm that you can call private Occam's razor. It has sample complexity that matches the non-private Occam's razor. And there's a question whether we can close the gap with non-private learning in the case of concept classes with small VC dimension. In particular, what happens if the concept class is infinite but has a finite VC dimension? Can we learn that privately? Okay. And another question is whether we, we didn't see all the details, but you can construct an efficient PPAC parity learner. So you could ask whether it's always the case that if you have an efficient PAC learner, there's also an efficient private PAC learner for the same concept class. Okay? And this is where I go to the second hour of this presentation. Okay, so I want to focus again. When do we finish? At 3:30? 4:30? Okay. So I want to go back to this simple case of learning point functions. Okay, so you have, like, on the right, a picture of such a concept. The concept class contains 2 to the d, where d is the size of representation of a concept. It contains 2 to the d hypothesis concepts, and we have, without privacy, we can learn points properly with just order of 1 samples. With privacy, the generic construction gives us something that is logarithmic in the concept class, which in this case is d. Okay, so is this gap essential? That's the question that was also asked here. And the first theorem I want to show is that if we insist on 2 things, first, that this is a proper learner, so what we output is a point function. Secondly, that this is a pure privacy learner, then it's essential that the sample complexity is at least linear in D. Okay? And the proof is really simple. We've seen, sorry? Pure private means delta equals 0. So we'll use a very simple packing argument to prove this. Okay, we've seen John have taught us about packing arguments, so we can try to use it here. And here's the argument. Let's look at this database. And again, I'm doing something a bit informal. I'm mixing learning over the sample and learning over the distribution, or learning over the data and learning over the distribution. But everything can be breached. So let's look at this case where all the input points are located at x value I, and the label is 1. Okay? So this forces the learner to return this concept Ci with high probability, say with probability at least 1/2. Okay, we want it to be 1 minus beta, but at least 1/2. Okay, and this is true for all I. And you remember, like in the packing argument, we construct many different data sets for which the answers are, the good answers, the set of good answers are disjoint. In this case, the set of good answers is a singleton, it's only Ci. Okay, and for every I, we're getting a different set. The sets are disjoint, okay. Different singleton. So this is exactly what we want. And now, by group privacy, if we say put this input into the learner, it still has to output something that is good for this input with probability that is proportion that goes down exponentially with this epsilon and n. Okay, and there are So if this is our input, there are 2 to the d minus 1 bad outputs, and each of them has to appear when we feed the learner with this input with at least this probability. Okay, maybe I'm missing a 1/2 here, like this thing times 1/2. Okay, so we need this thing. So this is the probability of, this is a lower bound of the probability of producing a wrong output for this database. We need that to be less than 1/2. And when you do the math, you get that n has to be at least d over epsilon. Okay, just a very simple application of a packing argument. So this shows us that it's not a coincidence that we got this thing that the sample complexity for learning points is order of d. We cannot improve that unless we relax our requirements. And remember that here, this is proved only for the proper case. So we insist on outputting a point function, and for pure private, differentially private learner. And we'll look into these 2 things and see what happens when we relax these requirements. Can we gain by having a non-zero delta, and can we gain by allowing the learner to output something that is not a point function? Yeah? Because I said that it must be that the output is Cj. If it's not proper, then maybe there are many other, for instance, the function that, the concept, the hypothesis that returns 1 all the time is also a good hypothesis for this. Okay, it's also consistent. Okay, so let's do this first thing and show that moving from a proper learner to improper learning actually can help us. And this is surprising because people have looked at improper learners also in the classical learning setting without the requirement of privacy. And the reasons for moving from proper to improper learning are computational. There are problems for which it's hard to find a consistent hypothesis in polynomial time, but then if you, in a sense, you expand your hypothesis class, you are allowing choosing hypothesis from a richer class, then the problem becomes tractable. But in terms of sample complexity, like in terms of information, if you don't care about computation, there's never a reason to move from proper to improper learning in classical learning theory. Okay? Whereas here, the only arguments we made are information theoretic arguments. We didn't look at computation complexity at all. And the reason for the gain in, and there is a gain in moving from proper to improper learning. Okay, we'll show that. So it's an essentially different phenomena from what we have in classical learning theory. So, what tools do we have? We don't have much. We have this private Occam Razor algorithm, and the problem with the private Occam Razor algorithm is that we use the exponential mechanism, and then to get correctness, we needed to take sample complexity that is logarithmic in the size of the concept class. So maybe we can try to squeeze our concept class and get a concept class that is much smaller. And then when we apply the exponential mechanism, we won't have to pay so much in sample complexity. Okay? And here's a trick how to do that. We're going to choose our hypothesis class, the class from which we're choosing, the outcome, we're going to choose it independently of the input, and we're going to choose it at random. So we don't look at the input, and we're choosing a family of hypotheses. It's going to be a small family. Now, if we're lucky, when we will see our data, one of these hypotheses is going to be good for the data, and the exponential mechanism will pick that hypothesis as an output. If we're not lucky, this will not happen. So we need to construct this random family in a way that with high probability, although we didn't look at the data yet, with high probability it is going to be a good hypothesis there. Okay, so we want it to be small, and there is a good hypothesis in this class with high probability. That's what we'll try to do. And I will construct here hypotheses that have long representation. You can get rid of that, but that's not the point here. So I'm going to select hypotheses in the following way. So hypothesis is just a very long string of bits. Like for every possible input, we say whether the answer is 0 or 1. Okay? And at every point x, we select it to be 1 with probability about alpha over 4, and 0 otherwise. So these are long strings of bits that contains many ones. About alpha over 4 fraction of the positions are ones. It's very different from point function, because a point function is 1 only on one point of the domain. This returns the value 1 on a linear fraction of the points in the domain. It's extremely different. But I want to claim that if I collect enough of these, I'm okay. Okay? So I'll collect a few of these guys, something like 1 over alpha hypothesis. And this is going to be my hypothesis class. And now, we can replace this totally random selection with a pairwise selection. I don't want to get into that here. And now we have a very small hypothesis class. We can apply the exponential mechanism and choose the best hypothesis there, or something that is close to be the best hypothesis there. And that's enough. And to do that, we only need to select from a tiny class of hypotheses. You see, this is, where's the size? Here, 1 over alpha. So the number of examples we need to see is totally independent from D. Okay, this is what we wanted. We're getting something very similar to what happens non-privately, up to constants that depend on the privacy and accuracy parameters. Okay? So I want now to claim that this works. And for this to work, we know that the exponential mechanism works. Hopefully, you believe Katrina's proof. So all I need to show, so privacy, I'm getting privacy for free, okay? The only way I looked at my data is through the exponential mechanism. That's okay. I want to show that this actually gives utility, that this is a good learner. And for this to be a good learner, I only need to show that with high enough probability, there's going to be a good hypothesis in this class H of hypothesis. Okay? So that's the claim. Let's say with probability at least 1/2. You could plug in better parameters here. So we can make the probability 1 on beta, but let's say with probability at least half, this set contains a hypothesis that has small error, say alpha over 2. Here's the proof. As you see, I don't need much space for the proof. Conditioned on the hypothesis getting the right value on the point J of the target concept. Okay? Conditioned on that, the error only comes from what happens in the places where the target concept gives the label 0, but H gives the label 1. But because we chose on every point H returns 1 with probability of alpha over 4, in expectation, this error is bounded by alpha over 4. Okay? Using Markov, we can get that this error is more than alpha over 2 with probability less than 1/2, using Markov's inequality. And again, conditioning on the jth location being labeled 1, but this only happens with probability alpha over 4, and hence we're getting that overall, if we remove this conditioning, the probability of the error is bounded by alpha over 2 is at least alpha over 8. So this tells us how many hypotheses like that we need to take. Roughly 1 over alpha will make, if we take 1 over alpha hypothesis, I don't know, 8 over alpha hypothesis, then we expect that one of them will be fine. Okay, if we want that to happen, we'll probably do 1/2. I guess we take 16 over alpha or something like that. Okay, so it's very simple, but there is something unintuitive here because we're learning improperly, and the hypotheses that we output are very distinct, very far from point functions. Okay, so sometimes it makes sense to do it. If you think about it in retrospect, there is something intuitive here in the sense we're hiding that point with a lot of clutter, but you need to work formally in order to show that this actually works. What's the question? So if the domain is of size 2 to the d, you're getting 2 to the d times alpha over 4 ones, tons of ones. Yeah. If you just guess one of them, you're successful with tiny probability. Yeah. Okay, so this thing can be generalized to the idea of representation of concept classes. Let me go very fast on that. And it gives learners for these three, in the case of pure privacy, as follows. The representation dimension that I did not define, a generalization of the idea that I showed, exactly characterizes the sample complexity in the case of pure differential privacy. It is sometimes useful, we know only one case, or a few cases that are very similar to each other, all look like these point functions where it reduces the sample complexity from d, that's t is 2 to the d, to a constant. But for thresholds, Feldman and Shao showed that we're not gaining anything by using tricks like that. Okay, so maybe we're stuck here. So I said there were two qualifiers in this theorem. One was that we were using proper learners. The other was that the learner is a pure privacy learner. So let's see if we can do better when we move from pure privacy to approximate privacy. Approximate privacy means that delta is non-zero. We allow delta that is non-zero. And let me summarize results that we have there. Unfortunately, we don't have a general result in the case of approximate differential privacy. We have very scattered information here. For points, we can use techniques that are based on the ideas that Adam presented yesterday, actually, based on one of his algorithms that shows how to learn points properly with a constant sample complexity. And for thresholds, what would you guess the answer should be? Adam? For thresholds, we're getting this very strange thing. Learning thresholds properly with approximate differential privacy, we have an upper bound that looks like this. Let me pass it for you. Log star of t is, log star is the function. If you have a calculator, you put a number, how many times do you have to press the log function until you get a number below 1? Okay. Usually not more than 5. I mean, if you put in the size of the universe, you get 5 or 6. So it's a really, really, really slowly growing function, but it is growing. So we have currently an upper bound that looks like 2 to the order of log star of the domain size. Okay. You would suspect, as I did for a long time, that this is very far from the right answer. So something that grows so slowly, you would suspect it has to be a constant. But we also have a lower bound, which is almost matching up to an exponential gap here, which is log star of the domain size. Okay, this is one of the places where you have an exponential gap, but it's almost meaningless that this is an exponential gap. Okay, so I hope I'll have time to show some ideas here. So let me skip this. You have it in your notes, and I think it's easy. It's using the ideas that Adam presented yesterday. And let me speak a little about this question of learning threshold functions. Okay, and I think this is where I'll conclude. If you remember my story, my motivation was I wanted to study scurvy. Why would you like to study these functions? Okay. One is mathematically it seems very fundamental and simple, and you know we should be able to know what the answer is here. Shouldn't be too hard, maybe. But furthermore, you can show that it is equivalent under differential privacy to a collection of other problems. So in the in the exercise sheet that we gave you yesterday, there was a question relating this seemingly stupid problem of given a collection of numbers, just give me an answer that is something between the minimum and maximum. Looks like totally useless. But these two problems can be shown to be equivalent under differential privacy, under the requirement of differential privacy. And furthermore, they are equivalent to some other stuff, like distribution learning. This is the problem of answering all threshold functions simultaneously. So we discussed this question when I spoke about the binary tree algorithm. So it's exactly the same problem, but here we're looking at it with epsilon delta differential privacy. Query list of threshold functions, computing the median that was in your exercise sheet, and this seemingly stupid problem of interior point, where you're given a collection of points and you just need to output something between the minimum and maximum. Like without privacy, this is a totally uninteresting problem. Yeah, you just output the first number you get in your input, and you go to the sea, to the beach. But with privacy, it turns out to be at least somewhat challenging. So let's see what happens when we try to solve interior point with approximate differential privacy. And this is what this problem is, what gives us this omega of log star domain size sample complexity. Okay. So I want to give the essence of this proof, and it's going to be an inductive argument. So I'll begin with the basis of the induction. It's going to be an inductive argument saying, suppose we cannot solve it with sample complexity something under domain size t, then we'll prove that we cannot solve it with sample complexity slightly larger, with domain size much larger, and it's going to be by constructing a reduction showing that if you can solve it with the larger t, you can also solve it with a smaller t. Okay, so let me begin with the basis case. Let's assume that the domain size is just 2, okay? 2 or more, but 2 will suffice. And I want to claim that you cannot answer this if you just have one sample. Again, without privacy, it's trivial. You just copy your input to the output, and you're done in this case. And this is the reason. This is because of differential privacy. So this is one possible input to the algorithm. So the point is 1, and in this case you have to output 1. That's the only solution between minimum and maximum. And in this case the point is 2. The input point is 2, so you have to output 2. But differential privacy doesn't allow us to distinguish these two cases. So if you fix epsilon and delta not to be too large, then on the left, let's say you have to output 1 with probability at least 3/4, and hence, because of differential privacy, you have to output 1 with probability more than 1/4 on the right, and this means that you are not giving like a good answer on the right hand instance with probability 3/4. Okay, so if you output a 1 here, then it's the wrong answer. So if epsilon and delta are not too big, you're getting that. Okay, is that clear? And now we'll do the induction. We'll assume that we have a differentially private mechanism, M, for solving the interior point problem over domain of size t of n plus 1. We'll see how t grows with n plus 1 samples. And from that, we will yield an approximate differentially private algorithms that works for the smaller domain, t of n, with just n samples. Okay? And the domain size is going to grow exponentially in every step. Okay, so it's going to be some number b. Let's forget the dependency on n, just a technical thing. Some number b raised. So let's think about this as 2 to the t of n. So this is, it grows like a tower of exponentiations, like a tower of n. Okay. So let me show you the essential parts of this induction step. So we're given a mechanism that gets n plus 1 inputs, okay, in the larger domain, and manages to output an interior point. Okay, that's the output of the mechanism. Let's say it succeeds with high probability. We will construct from this mechanism another mechanism that is also differentially private. But we're going backwards. So this mechanism now gets inputs from the smaller domain, t of n. Here it was t of n plus 1. And it has less inputs. Here we had n plus 1 inputs. Here we only have n inputs. Okay? And it will manage to output an interior point of this input set. Okay? So this is a bit strange. So let me try to go over it not too fast. So we have this input. These are numbers in the smaller domain, okay? And we need to create the inputs for this mechanism in the larger domain. And this is how we do it. We first generate a number, okay? It has this number of digits. So this is digit by digit. I'm choosing a number at random, okay? Each digit is chosen uniformly at random, say from the basis B. I said that that's just a technical thing that has to grow with n, but I'm not going to get into that detail. So this is a number. Each digit here is from the basis B, and we have t digits, so it's a number of, in this domain of this size, okay? Okay, and remember that this is exactly what t of n plus 1 is, okay? So in particular, we could put this number as input to the mechanism M, okay? Or numbers of this length are good inputs for the mechanism M, okay? Now, we will create the inputs. The first one is just this number, okay? This is Z0, the random number that we created here. And then we will create Zi in the following way. Let's take Xi, let's say X1, okay? It's a number in this range. Remember, we have this number of digits here. So we can take the prefix from this random number, the Xi first digits, and write them down. And then append random digits at the end of this, okay? So I'm beginning with, let's say, a small number xi, and I'm getting a huge number, like the number of digits here that are copied from the random string is xi digits, and then I fill them up with random digits, okay? And so on. This happens for all xi. So what I have here, I created n plus 1 numbers, really huge numbers, as input to this mechanism M. I feed them in, I'm getting an interior point, and what I do with it, okay? Sorry? Oh, yeah, I guess this should have been Y0. All these. Oh, let me see. Am I missing something here?
You have eyes at the end. You said 0, you have 0.
Oh, sorry. Yes, you're right. Yeah. So Y0. Yeah, I have many strings like that. Yeah. Sorry, I confused you. I have many strings like that. Okay. What's that? For each I. I have n plus 1 digit strings like that. Y0 is just the Z0 is just a random string, and in Zi I copy a prefix from Y0 and then I fill it up with a random suffix which I take from the Yi's. Okay, so the description was correct, but it didn't match what's written on the board, on the slide. And then we need to generate an output not for the interior point of this set, but of this set. And this is how I'm going to do it. I will look at Z tilde, the output here, and count on how many digits it agrees with this string, Z0. Okay? This is going to be my output. Okay? So I need to prove two things. Okay? What are the two things I need to prove? Privacy and accuracy. Okay, as usual. Privacy is extremely easy to prove because we're just post-processing. So we're operating on each input separately. We're transforming each input into a different input. We're pushing it through M, and then we're post-processing it. We're getting privacy for free. So this is easy. we're just, if you're worried about this transformation here, we're just translating each input to something else, but we're doing it independently on each of them. Like we chose some encoding of the inputs, and we're processing each of them separately. Okay, so differential privacy is something that I'm getting for free here. That's easy. Now I need to show that this actually works. This, and obviously it does, isn't it? It's such a simple algorithm. Okay, so I need to show that the outcome is larger than the minimum and smaller than the maximum. Okay, if that is with high probability, if that is the case, then I'm done. Okay. Now, to show that it's larger than the minimum, it's not hard. All these z numbers, okay, they share a prefix, okay, of length the minimum of x1 to xn. Okay, all of them copied the prefix from y0. Okay, so no matter what happens, z tilde should also have to share this prefix with the string y0. Okay, so obviously we're getting x tilde, which is larger than the minimum. Okay, by why would it be not larger than the maximum? Okay, what do you think? What tool can I use here to prove that it's not larger than the maximum? Okay, you can of course pick in your slides. And this is a place where we're using differential privacy to prove utility. Okay? I want to say that because of privacy, this z tilde cannot include cannot include digits beyond the max of xi, beyond that location. Because if that happens, we're revealing information about y0 at that location that the other inputs are not revealing. Okay, and differential privacy doesn't allow us to do that. Okay, so if it turns out that this x tilde here is more than max here, then we're revealing some digit from z0, which is a digit from 1,0, that only appears in one location. Okay, differential privacy allows that to happen with only bounded probability, something like 1/b times the factor of epsilon e to the epsilon plus the slackness of delta. Now we have to be careful in how we choose b so that thing is kept small, and this is the technical issue about this, the choice of the basis b. Okay, so here we use privacy for getting the correctness. Okay, cool. So I know this is a bit hard to digest. So maybe the best thing I'll do now is, and I only have 4 more minutes. So there's a little more in your slides, which I will skip now. I want to mention one thing. I only looked at here in this session, we only looked at the question of sample complexity, but you could also ask what happens to computational complexity. And this is again a place where we can use crypto to the detriment of privacy, as John will do tomorrow. And the paper by Mark Bahn and Mark Zandri shows that a variant on this idea of thresholds, a concept class that is easily learnable without privacy, but with privacy, it becomes intractable. Okay, this is really a beautiful result. It uses the concept of order revealing encryption. The learner can compare encrypted numbers but learn nothing else. Okay, so let me finish with these two slides. Why do we study private learning? One reason is that real-world implementations of learning can lead to loss of privacy. I think Vitaly gave a very convincing argument there, probably more convincing than my argument with Shiva's data. So recall his talk. Also, let me repeat a few points that he made really beautifully. We have to distinguish carefully between what is a privacy breach and what is not privacy breach, okay? I liked Vitaly's distinction of prediction of and inference about individuals. And I also recommend looking at Frank McSherry's blog posts where he distinguishes between what he calls secrets about you, which are things that you thought are secrets, but if I learn them about other humans, then I also learn them about you, and what he calls your secrets, secrets that are specific to you, okay? And furthermore, learning is a basic task that abstracts many of the tasks or the computations we would like to perform on sensitive individual data, so it's important to study that. It's a test bed for many ideas. I only had a chance to mention a few of them. The fact that you can use improper learning in a useful way, the fact that there is a difference between, a striking difference in some cases between proper and improper, pure and approximate differential privacy. Of course, these are not the only examples. There are other examples. It's intimately related with differential privacy. Some techniques, some algorithmic techniques that we use in differential privacy are borrowed from developments in learning theory. And furthermore, what I spoke about earlier today, the fact that differential privacy generalizes also suggests this intimate relationship with learning theory. And as I said, sometimes it's may be useful to use differential privacy even if privacy is not your goal. Okay. What have we learned? Back learning exhibits a lot of complexity, and there are a lot of interesting open questions if you're interested in finding research topics. Even you saw that we have limited understanding even for very simple concept classes like points and thresholds, and we need to build our understanding further. So this is really, if you're interested, a point where you can look at problems. There is a lot of applicable strategies. Full picture is only for the pure differentially private case. Okay. Crypto again used for showing hardness. We'll hear John speak about that a lot tomorrow. But there's a question whether we can use crypto in a positive way for differential privacy. And I think this is where I'll stop. Okay, you have some more references in the slide deck.